Hello everyone. So today we are going to do something completely new and different. And I will be learning assembly basically. I've been reading assembly last week. I learned how to do some basic stuff, how to make little programs, even a function. So this is what I will keep working from. So making functions in assembly though. So last thing I did was a basic function like a using the C standard of functions, and now I am going to do this recursive function in assembly. So let me set up my development environment. There it is. So let me make a new program here, like let me do it. Let me set up just my makefile power func into func. There it is. And we are going to basically just clean all this thing. Okay, there it is. So I already have my makefile, and let's start reading. So this is going to be a stream where you will watch me read stuff mostly. Like it will be me reading stuff. Let me check something. Okay, it's working. Yes, I did it. I wanted to check that. So let's get into it. Recursive functions. The next program will stretch your brains even more. Oh, that's going to be something because I remember the last exercise I had to do in the last exercise I did was a bubble sort in assembly, but using a function, and it was quite hard for me. I have to be honest; it was not easy. So, if it says to me that the next program will stretch my brain even more, I am quite scared. But I like challenge, so I am sure that someone with experience in assembly will look at me and see you're having issues with the this basic stuff. But anyway, so the program will compute the factorial of a number. Oh yes, that's a classic. Using a recursive function to calculate a factorial is a classic one. A factorial is the product of a number and all the numbers between it and 1. Yes, I know. For example, the factorial of 7 is 7 product 6, product 5, product 4, product 3. Okay, yes, I know what a factorial is. And the factorial of 4, yes, I know it. Now, one thing you might notice is that the factorial of a number is the same as the product of a number and the factorial just below it. Yes, that's a property of factorial numbers for anyone that learn about it in mathematics. It's that. But the factorial of 4 is 4 times the factorial of 3. Yes, the factorial of 3 is 3 times the factorial of 2. Yes, we get the point. The factorial of 1 is 1. This is the type of definition. This type of definition is called a recursive function definition. That means the definition of the factorial function includes the factorial function itself. However, since all functions need to end, a recursive definition must include a base case. The base case is the point where the recursion will stop. Without a base case, the function will go on forever carrying itself until it eventually runs out of stack space. Yeah, I know what's going to happen. In the case of the factorial, the base case is the number 1. When we hit the number 1, we don't run the factorial again. We just say that the factorial of 1 is 1. So let's run through what we want the code to look like for all factorial functions. The funny thing about this is that I know how to do this in like 1 minute with any other programming language, like high-level programming language. But I feel that with assembly this is going to be really hard. I will be using an example though from the book, but it's going to be really hard probably for me at last. Examine the number is the number 1. If so, the answer is 1. Otherwise, the answer is the number times the factorial of the number minus 1. Yes. This would be problematic if we didn't have local variables. In other programs, storing values in global variables working fine. However, global variables only provide one copy of each variable. In this program, we will have multiple copies of the function running at the same time. All of them needed their own copies of the data. Since local variables exist on the stack frame and each function called get its own stack frame, we are okay. Let's look at the code to see how this works. Okay, let's just look at this. Okay, there is no global data in this program. This is a need unless we want to share this function among other programs, but it's interesting to know that. Okay, so we are going to calculate the factorial of 4, I believe. I don't know what's that. I know what the calculus function, but that add long 4, I don't get it that pretty well. Why? Yeah. The factorial takes one argument, the number we want the factorial of, so it gets pushed. That's okay. Factorial returns the answer in EAX, but we want it in AVX to send it as our exit status. Okay, I know it. Yes, this is the basic kernel exit function in Linux. This is the actual function definition. Standard function stuff, we have to restore ABP to its prior states before returning, so we have to push it. This is because we don't want to modify the stack pointer, so we use ABP, yes. It moves the first argument to EAX. ABP holds the return address and 8 ABP holds the first parameter. Okay. I'm trying to remember how this actually went, but anyway. If the number is 1, that is our base case, we simply return n factorial. The n factorial just standard function return stuff. We have to restore the ABP and ASP to where they were before the function started. Return the function. This pops the return values. Okay, so let me see. Okay, I call factorial here. In case it's not the base case, otherwise decrease the value. We decrease the value of the parameter. Yeah, makes sense. Push it for our call to factorial, call factorial. EX has the return value, so we reload our parameter into ABX. I have quite lost here. Let me see. Multiply that by the result of the last call to factorial. Yes, that's where it's storing EX, which is good since that's where the return values go. So I guess I understand what's going on here, but I have some problem thinking about this call of factorial and how is this going to multiply 4, multiply for 3, multiply for 2, etc. in case I call the factorial function. So let me think what could be happening here. Okay, I understand we decrease the value, push it for our call to factorial, okay. So the thing here is that I don't use any parameter, it seems. There are no local variables in this function, it seems. So yes, I believe I do not understand this code exactly, but it will help. In my case, it helps me to actually run the program and experiment a bit with it to understand it better, more than looking at the code. So let's make this program. Let's make this program run with my terminal. There it is. Calculate the factorial function. Data. Okay, yes. Global data. Section text. We don't have a section, a text section item. This is very interesting because this is on need unless we want to share this function among other programs. Okay, that this is on need. Let's basically with here we push the number, the literal number 4 into the stack, I believe. So yeah, argument. Number. So yeah. Sorry. We call the factorial function. Yes. Okay, so let's recap. I am just writing code here, but now let's just take a look at what I wrote. Okay, so we don't have any global data, we don't have any text section. We use this in case we want our function to be used outside this file with other programs. Then the first thing we do when our assembly program starts, we push the number 4, that it will be the first parameter of the function factorial. We push this on the stack. And to just refresh my mind a bit, let's just take a look at how assembly function state frame, how this was supposed to be. There it is. There it is. So for example here, I don't use that kind of. Let me see another example that will help me more to understand. So those are the parameters, returns address, and MVP and SSP. So let me look at variables. Okay, there it is. It's actually helps a bit more. Let's do by Kali. Let me look at the best. Okay, this one actually stack frames are the foundation of stack memory. ASB, aka frame pointers, are unchanged reference point data stack. ASP, aka stack pointers, point to the next item on the stack. So AVP, it's basically AVP plus 4 is always the return address. ASP, it's basically the. I don't use this. I don't use save ASI. I usually start a local variable, and that's where I start. So let's actually how we format this in our book, because yeah, this is how we use it here. For example, I have my return address here, my all. Yeah, and ASP usually it's the end of the stack, right? The end of the stack, it tends to be. So no, this is not the way I tend to use this. Let me look at another more similar to what I do. Okay, this is probably what I do. This is exactly what I do. So basically, these ones are the parameters, if I recall correctly. Yes, those are the parameters. My save ABP, or basically previous pointer, and my ACP is basically at the end of the stack. So I have everything that goes go ABP plus, it's plus 8 and upwards, it's basically my local variables. Everything that goes like ABP minus 4 and forward, it tends to be my. So no, everything that goes ABP plus 8 and forward, it's my parameters of the function, and everything that goes like ABP minus 4 and less, it's basically my, how to call it, basically my local variables. And the last one is the return. No, it's not the return one. No, it's just everything. All of this is our local variables, and I do decide what is my return value, setting that up to AAX, I believe. Let me take a look at this. So yes, this my return value. It otherwise go into AAX. So AAX. So yes, in this case, my return value goes. Okay, I see what happens. Yes, okay, so it's making a bit more sense now. So let's go back to this. So basically, with push LIF4, I am moving that argument into my factorial, but I want to know exactly what it does. It basically will basically be moving that into. I know what's happening, but I want more information because I like to understand things like deeply, you know. So let's go by push assembly. What it does. The burst instruction places the current PC value onto the stack. This increments the stack pointer and not the current. So basically, I want to see how. What does the push does? Functions push and this is what I want probably. I am using Assembly X. Use it to add a new resource with more stack. Push and pop instructions in assembly language. This is going to help me a lot probably. Now I'm going to probably watch an article because I don't want to watch a video from another. Let's just look at an article, it's going to be better. Push pop assembly. Yes, recoil stack. See memory layout. Oh, I see. So basically the push instructions does both of the steps to add value to the stack. So there are two steps to adding a value on the stack. First, we have to allocate additional space on the stack by decrementing the ASP. Then we store the value in the newly allocated space. So before push ABX, after push ABX, current stack. Oh, I see. Yes, I know what's happening. It makes sense for me now. Yes, it totally makes sense for me. So that's why the negative values, like, okay, so this is explaining a lot of things. The ASP, so then first thing I do, I set my current ASP to AVP, if I recall correctly. Yes, I do it to keep the stack pointer. And everything plus like it's I learned that it's quite, I remember reading that this is actually the bottom, the stack is at the bottom, so when you go plus you are going like, it's like different. I mean the stack is not at the top of the memory but at the bottom of the memory, if I recall correctly, or something like that. Something like that it was. So yes, that helped me a lot to understand better how the stack framing assembly does work. So yes, this helps. I did some functions in assembly before, but this helps me to understand exactly what this push forward does. Basically, it oops my. Let's use the open world. I mean, I like to learn by using a whiteboard, and like imagine I am in some kind of classroom, if that makes sense. So basically when I do something like, let's draw my stack frame. Or this is like, let's call this a stack. Yeah, I know my type, my letter is not the best. Push. If I basically do push like 4 like that, this is going to do the following thing. I'm going to have like I'm going to have like the number 4 here, and I'm going to have my let me see what. Or AVP to its prior state before. I'm sorry. Before returning, so we have to push it. So I can ignore that step and basically should say, okay, I'm back. Can just basically be like, okay, this is where my ISP is pointing into this address, and this should be the red address, I guess. I don't know if this is exactly the red address, but I believe that this is what happens when I push. Then, of course, inside the function, I push the other pointer and blah blah blah, but that's okay. So let's go into the code again. I know what the push does now. I go the factorial, etc. etc. Scripts the parameter that was pushed on the stack. This part I do not understand very well what's going on here, because it says it's add along into the ASP register pointer, or so the ASP register, but why it's doing that? Why I am adding 4 into that register? Scripts the pattern was pushed on stack. It's moving there. Oh, because along takes 4 bytes, I guess. So it's moving 4 bytes. I am quite lost, not gonna lie. Script the parameter was pushed on the stack. Actually, let me check something, because what is exactly the meaning of script? Data cleansing, also referred as data cleaning or data scrubbing, the process of fixing, incomplete, duplicable, or otherwise erroneous data in the dataset. So it says to me that the ASP register is erroneous and I have to fix it manually. But why? Why I have to do that? Okay, the best thing I can do is to just keep writing this code, compile it and test it, experiment a bit, and after that I will keep reading this. I usually like to experiment before just read, because this is not this is not like reading a literature work, or some kind of another not technical textbooks. I actually need to do some practice and experimenting to understand what's going on, and science assembly, it's quite hard, not gonna lie. It's really quite hard for me, and that's why I like it, because it's teaching me how the computer works, mostly the CPU and the memory. It's worthwhile to take the time to read this kind of books and experiment slowly and with patience. Patience is like the driver of knowledge. Okay, so what more? Okay, this is basic kernel stuff. So this is classic in assembly, like just, and that's in the programs I am doing right now. The very basic programs I am doing. Call the kernels exit function status or function. Okay, that's basically what it does. I am sorry that you are hearing that. It's because I have a cold. I don't know what I have. It's been maybe a flu. Yes, I have maybe a flu. But it's okay. Nothing better than learning assembly with flu. You know, something I do notice is that I started programming with C like 10 years ago, a long time ago, and getting pointers was quite hard for me, I remember. Like, getting the fact about how memory works, pointers work, all that of values by reference, parameters by reference or value, etc., etc. I remember that being a very strong headache for me at the time. Now I do realize that if you want to understand C, you probably want to learn at least the very basics of assembly first. I am not saying that you should be an expert in assembly, because I am not the expert in assembly, but at all I am just learning it right now. But by just learning the basics of assembly, I do realize that many of the concepts of C programming language are just there in assembly. It's just basically there. And if I don't, if I recall correctly, C was created actually to be as an human readable version of assembly. Well, actually, assembly is a human readable version of machine code. So basically, assembly is a human readable version of machine code, and C it's a more human readable version of assembly, I guess. Okay, so let's go into the factorial function now. This is the actual function definition. Okay. This, sorry. This is the actual. This is the actual factorial definition. Type factorial function. Oh no. So basically with this we do increase the stack frame, standard function stuff. We have to restore to its prior state for returning. So we have to push it. Out. Yes, of course. Okay, so I have to add another tabulation more here. Oops. First argument to what's the return. Okay, so let's take a break here and let's analyze what we are doing. So we are actually defining the function in assembly here. It is, if someone tells you that you can't do functions with assembly, it's someone that did not read any book or basic manual was in assembly at all, because I found some people doing jokes about assembly saying that it does not have functions, but it does have functions. Otherwise, how the hell do you program something without functions? I mean, you could, but you shouldn't. But okay, so basically the first thing we do is, this is the part that actually I do not understand well, because I know that we here restore that CPU register to its prior state, like it says, but I don't know why we have to do that in the first line of the function. And I am sure the book explained this before. Let's go a bit back here. Save all base pointer. Here is a good example of what happens in a function. So yes, this is an example of a function structure. Oh, I know what happened. Basically, the ABP holds the return address, I guess? No, I don't think so, though. Let me just check that, please, because what happens at the end of the function, though? Let me check what happens at the end of the function. And power. Restore the base pointer. Okay. Okay. Restore the stack pointer, restore the base pointer. Okay. Okay, so basically I have to restore the base pointer because the return address is located at ASP 4, like 4 ASP, I believe. make stack pointer base pointer. So probably pop AVP basically should remove all of this from the stack, I guess. Take all of this and leave the ESP like here. Let me check something first. Yes. So basically this is the ASP pointer, it's a return address. Oh yes, so basically that's what it does. Yes, that explains a lot. Yeah, so that's basically what it seems to be doing. Basically, when I do pop ABP, basically I should restore this stack pointer how it was originally, so the return address, so ASP points to the return address. So that the assembly knows that. Actually, assembly knows, the CPU knows, or the machine knows that when the call ends, it has to return to that section of the code. So yeah, that helped a lot. That did help a lot. Always good to learn something. So yeah, this is usually how I would like to learn to read a book about something like this. That I know it's complex to me. It should take my time, Google some stuff, experiment, take a look at the code, etc., 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 etc. Let's move the first argument to AAX. What's the return address? Yes, that's interesting. Yes, that this does the check that if the current argument is one, that is base case, and we simply return one is already in the exact return value. Yes, perfect. Nice conditional jump. Otherwise, decreased value. Why this push though? Push it for one. Oh yes. Does this push the value then and not the memory address? It seems that it does. Look at this nice recursive function. But factorial. It's store, not sort. Store. Which is good. Thanks. That's where return values go. Classic end of function in assembly stuff. Yes. Okay, so basically this is my function and this should be already working. So if I do basically make it, the error code it returns is 24, and 24 should be the factorial of 4. So if for example I do 1, the error code must be 1, yes. If I do 2, the error code must be 2. If I do 3, the error code must be 6. If I do 4, the error code will be 24. If I do 5, the error 24 product 5 should be like 120? It should be 120 though. Yes, I was right. Okay, so the factorial function works. So this was a nice piece of work to do in assembly. I took my time to do this example from the book because I wanted to understand what I was doing. If I do not understand, it makes no sense. So I will actually help me a bit to understand with my open board here, my whiteboard. So basically when I call the factorial function, let's just I will do some very basic stuff and it's going to be like when I have my factorial function and I do call factorial, the code must be like this. For example, let's say that I start with the argument like my param, or let's could be for parameter. My param starts with 4, right? So I got my param form here, blah 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 blah. I go like this, my param turns into 3. Blah 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 blah. My param turns into 2. Blah 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 blah. My param turns into 1. And in the case of 1, I just return when it's 1. When it's 1, I do return. And when I return with 1, it will be like, okay, 1, dot 2, dot 3, dot 4. This is going the order of execution, I believe. So let's try to make this in a more detailed example. Oh, I did something I shouldn't do. Now the open bar is going to be there, just broken. So let me keep the open bar. Okay, so that's interesting stuff. I will delete it like this. I have to remember what is the idea of this process. It's like this. There it is, yes. So yes, it was like that. It was like that indeed. That was the idea of the process. So we made the factorial function, but I like to like deep a bit further into this. So let's see factor recursive from Assembly X86. Let's just ignore the assembly part though. Okay, yes, this is exactly what I wanted. I found exactly what I wanted, what's going on here. So yeah, basically we got factorial 4 is going to call 5, sorry, we have factorial 4 is going to call 4, factorial 3 is going to call 3, factorial 2 is going to call 2, factorial 1. Then it goes the return process. It's going to be 2 product 1, 3 product 2, 4 product 6, 6 product 24. Okay, it is exactly what's happening. Okay, that helps a lot to understand. So assembling can run it with these commands. I already assembled my stuff. This should give you the value 24. 24 is the factorial of 4. So you can test it out itself with a calculator. Yes, I know how to test that. So I actually want to do something though, like what happens if I terminal like yes. Okay, I know, I get it. It's working. So this will give you okay. I'm guessing you didn't understand the word code listing. Yes, that's true. Let's go through it a line at a time to see what is happening. Start push for corporate. Okay, this program, I'm sorry. I'm quite sick, it seems. Okay, this program is intended to compute the factorial from number 4. When the programming functions, you are supposed to put the when programming functions, you are supposed to put the parameters of the function on the top of the stack right before you call it. Yes, I learned that before. Remember, a function's parameters instruction puts the given value at the top of the stack, a long value. The call instruction then makes the function call. Next, we have these lines. Add long, and move long. Add long, literal number 4 into the ASP CPU register. Interesting. Move long, EAX register into EBX register. It's more a copy than a move, but anyway. And then move long, that's actually a copy. Literal number 1 into EAX. Yeah, this is basically the last two ones. The first one is the one that I am quite confused about, but the other ones I don't understand. The move EAX into EBX, it basically moves the function return value into the error code when I exit the Linux. When I exit my program, moving the 1 into the EX, it says to the kernel in Linux that it should exit the function. This takes place after factorial has finished and computed the factorial of 4 for us. Now we have to clean up the stack. The add all instruction moves the stack pointer back to where it was before we push 4 onto the stack. Usually I always clean up your stack parameters after a function call return. Okay, so basically it cleans the stacks. Okay. The next instruction moves EAX to EBX. What's EAX? It is factorial's return value. It is the value of the factorial function with 4 as the parameter. 24 should be your return value. Remember, return values are always stored in EAX. We want to return this value as the status code to the operating system. However, Linux requires that the program exit status code to be stored in EBX CPU register, not EAX. So we have to move it. Yeah, this I know what's going on there. Then we do the standard exit system call. The nice thing about function calls is that other programmers don't have to know anything about them except its argument to use them. Yes, they provide standardized building blocks from which you can form a program. They can be called multiple times and from multiple locations, and they always know how to get back to where they were. Call pushes the return address onto the stack. Yes, that's why we have to restore the stack pointer just before the function ends, because otherwise the function will not know where to return. These are the main advantages of functions. Larger programs also use functions to break down complex pieces of code into smaller, simpler ones. In fact, almost all of programming is writing and calling functions. Let's now take a look at how the factorial function itself is implemented. Before the function starts, we have this directive: type factorial function factorial. The type directive tells the linker that factorial is a function. This isn't really needed unless we were using factorial in other programs. We have included it for completeness. The line that says factorial gives the symbol factorial the storage location of the next instruction. That's how call knew where to go when we said call factorial. Yes, basically it's an alias of the memory address. And call says call that memory address, I guess. The first real instructions of the function are push long ABP CPU register and move long ASP to ABP CPU register. As shown in the previous program, this creates the stack frame for this function. These two lines will be the way you should start every function. Yes. Okay. The first one basically save the... I forgot what I did. Okay, doesn't matter. The next instructions is move long 8ABP to AAX. This use base pointer addressing to move the first parameter of the function into EAX. Yes, let's remember that for ABP it's actually the return address, and the parameters of the function start from 8 and upwards. Remember, ABP has to be ABP has the old ABP. For ABP has the return address, and 8 ABP is the location of the first parameter of the function. If you think back, this will be the value 4 on the first call, since that was what we pushed on the stack before calling the function. As this function calls itself, it will have other values too. Next, we check to see if we have hit our base case as parameter of 1. If so, we jump to the instruction at the label n factorial, but it will be returned. It's already in EX, which we mentioned earlier, in where you put return values. That is accomplished by these lines. Here, it basically checks each one basically equal to... Well, actually, it does not check that. Compare the values of 1 with EAX, and we jump in case they are equal. Like 1 is equal to the value stored in EAX. And since we move the first parameter of the function into EAX, that's basically checking if 1 is the value of my function parameter. And since EAX already contains the function parameter, in this case we can just simply leave it like that and return the function, since EAX already holds the value of 1. If it's not our base case, what did we say we will do? We will call the factorial function again with our parameter -1. So first we decrease EAX by 1. Dec long stands for decrement. It subtracts 1 from the given register or memory location, EAX in our case. Inc long, it's the inverse. It adds 1. After decrementing EAX, we push it onto the stack, since it's going to be the parameter of the next function call. And then we call factorial again. Push long EAX, call factorial. So yes, we push EAX as the parameter of the next call of factorial, since EAX holds the first parameter -1 right now, or our original call in factorial. Okay, now we have called factorial. One thing to remember is that after a function call, we can never know what the registers are except ASP and ABP. So even though we have the value we were called with EAX, it's not there anymore. Therefore, we need to pull it off this. We need pull it off the stack from the same place we got in this first time at 8 ABP. So we do this. Move 8 ABP to ABX. Now we simply want to multiply that number with the result of the factorial function. Sorry. I'm sorry. Okay. If you remember our previous discussion, the result of functions are left in AEX. So we need to multiply EBX with EEX. This is done with the instruction emul long. Okay. This also stores the result in EAX, which is exactly where we want the return value for the function to be. Since the return value is in place, we just need to leave the function. If you remember, at the start of the function, we push ABP and we move ASP into ABP to create the current stack frame. Now we reverse the operation to destroy the current stack frame and reactivate the last one. Yes, basically this is a standard end of function stuff. So basically we recover our original stack, so the function, basically the ASP register points to the return address of the function. Now we are ready to return, so we issue the following command read. This pops the top of the value of the stack and then jumps to it. If you remember our discussion about call, we have said that call first push the address of the next instruction onto the stack before it jumps to the beginning of the function. So here we pop it back so we can return there. The function is done and we have our answer. Like our previous program, you should look over the program again and make sure you know what everything does. Look back through this section and then previous sections for the explanation of anything you don't understand. Then take a piece of paper and go through the program step by step, keeping track of what the values of the register are at each step and what values are on the stack. Doing this should deepen your understanding of what is going on. Now concepts. What are primitives? What are calling conventions? Yes. I should take probably a pencil or a pen and a paper and start doing exactly that. I can do actually that with my open world. It's going to be quite the same. What are local variables and what they are used for? How do push L and pop affect the stack? What special purpose register do they affect? Okay, they affect the ASP register. What are local variables and what they are used for? They are useful mostly for functions, like having some variables that need, you have some functions that sometimes need extra data to work, and you want that data contained inside that function, not globally. Why are local variables so necessary in recursive functions? I am using local variables in recursive functions, actually. I did not at all. I did not use any local variables in recursive functions. I mean, my current recursive functions right now. I know that there are some recursive functions that can use local variables, but I don't know. What are ABP and ASP used for? Okay, so ASP is basically the very bottom of the, or top, I don't know, that's the issue here, of the stack frame, and ABP holds it's used like to do not modify or alter the original ASP register. What is a stack frame? I can actually look at this. What are primitives? Let's just Google at this. The goal of a primitive assembly is to combine the clip place. In computer programming industry, primitive is a term used to describe a fundamental data type or code that can be used to build more complex software or interface. For example, Java, a computer programming language, is made up of less complex data types such as Boolean, a primitive data. Okay. Okay. Write a function called square. Okay, we have a challenge here. Nice. Finally time to get our hands dirty. I would probably go to buy something to drink before doing this. Write a function square which receives one argument and returns the square of that argument. That's going to be easy. Convert the maximum program given in the section called finding a maximum value into 3 so that it is a function which takes a pointer to several values and returns the maximum. I already did that, I believe. I believe I already did that, so I can try to do it again, but I did that already. Write a program that counts maximum with 3 different lists and returns the result of the last one as the program exits status code. Returns the result of the last one. Explain the problems that will arise without a standard calling convention. Going further, do you think it's better for a system to have a large set of primitives or a small one, assuming that the larger set can be written in terms of smaller one? The factorial function can be written non-recursively. Do so. Oh my goodness. Find an application on the computer you use regularly. Try to locate a specific feature and practice breaking that feature out into functions. Define the function created and look at. Okay, so we are going to be dealing with files after this. I am just looking. I want to spoiler myself what comes next, but I finish with functions, standard, and special files. Oh, here it comes the fun stuff, it seems. I have to go through the function chapter to finally get into the fun stuff. Okay, oh my goodness, this is a mess. Okay, the fun stuff is also the hard stuff, so I am quite afraid of this. Type this program as to upper and then enter the following commands. Quite a mess though, you know, this is like, wow. Okay, so what goes after this? Reading and writing simple records. Is there some kind of input here? I am just a spoiler, doing some spoiler, sorry. Okay, this is part assembly gets really hard. I see, I was just in the easy stuff it seems. Ho ho ho! Developing robust programs. Sharing function with code libraries. I see. I want to see what I am going to look at here. I would like some kind of input, you know, like being able to input text and in the console, but anyway. Intermediate memory topics. Because yes, I read files and all of that, but okay. Actually, I could just do this and look at. I could look at basically the. Here it is. counting like a computer. High level languages. The first C program and blah blah blah. Okay, this is actually a nice book, and it's helping me to. It's going to make C easier for me. I mean, it's a book that I will probably reread again, but by now let's just do the exercises. So I'm going to take a break, and I will stop this video and continue later. I will keep continuing with assembly, but in another video. We will write that function that the end of the chapter requires us to move on. Actually, it does not require us, but I like to do the exercises, you know, because otherwise you can always just ask to ChatGPT or anything to should generate me this code and do not learn anything. But I don't want to learn, so I will do the exercises. So see you in a 30 minutes probably. And I will write those functions, and then I will be done with assembly for today probably. Enough assembly for one day. So goodbye and thanks for staying here.